Hi, I'm Todd Mullen, and you're about to watch the introductory video for Math 1910. Okay, let's get started. We are here to learn Math 1910, Introductory Calculus, so we're doing this first lecture to get us prepared for it. In Introductory Calculus, we are talking about rates of change. These are the words that you're going to hear over and over and over again. And we're going to talk today first off about what is a rate of change, just filling in my letters there. So it's how quickly something changes. We have looked at functions in the past. We'll be making the assumption that with this being an introductory class, your mathematical experience will be grade 10, 11, or 12, or something equivalent to that. So we can talk about the functions that you've looked at in the past, linear functions, quadratic functions, trigonometric functions. Well, that's about it, not really much more than that. But we're going to talk about how those can be related to what is called a rate of change, whereas those things may measure where something lies. So let's look at an example. For instance, we are quite familiar with looking at things like the trajectory of a ball as it goes up and then it comes down. And you may remember answering questions that say something like, well, at what point was it at its apex? At what point was it at the highest? What was that x value? With that being the x-axis and that being the y-axis. Well, at what point was it at its highest? At what point did it actually touch the ground? Those different types of questions we ask. But something that we don't ask in high school typically is at what speed was the ball moving? Or how quickly was its position changing? At what rate was its position changing? Answering that type of question really cuts to the core of what calculus is. So that is the type of question that we're really going to start attacking today. We're going to try to figure out just how we can use a new concept that we'll talk about today, limits, to reach such an idea of how these rates of change can be applied to the functions that we tend to be quite familiar with. So I'm going to start by just shifting this to the left, and we're going to talk about the functions that we're familiar with, a bit of rehashing some old stuff. So the first thing is polynomials. Now, polynomials, they take some very similar forms. These should look familiar to you. Y equals mx plus b, that's kind of our first equation that we learn when we're graphing things. Equivalently, you can change the letters around. The names of the variables don't matter so much. Y equals ax plus b is common. Sometimes you'll see the capitalized form with y equals capital AX plus b. But it's all alluding to the same idea, something that is going to look roughly like this. It's a straight line that cuts throughout the Cartesian grid. And of course, plot your x and y. It's very good to be thorough when we're doing math so that people know what each axis represents. So y equals mx plus b, ax plus b, ax plus b, however you want to write it. But polynomials are so much more than just these linear functions. You can also get into a quadratic function. They tend to take the form y equals ax squared plus bx plus c, and there are other forms. And I'll write up a cubic function as well, but we get the idea of what a polynomial is. Ax cubed plus bx squared plus cx plus d, and you go on and on as the degree increases. The degree, of course, referring to that leading power. So here, that leading power, it could be just called 1. Here it's 2, here it's 3, and it can go as high as you want, honestly. And they all create different looking graphs. If you want what a parabola looks like, which is a quadratic or a second degree function, of course we would recall, if I label that x and y, that it may look something like this. That's an example of a parabola. Of course, there are infinitely many different parabolas I could draw. Or a cubic function. We maybe have a recollection of a cubic function as looking something like that. So hopefully this is revisiting some ideas that are rattling around in your head of the different polynomials that we've gotten used to knowing up to this point. Note that the word slope was quite unique to the linear situation. We always learned that m means slope. Now we'll touch on this in a few minutes, but this is very much going to hit to the core of our idea of rates of change. We are going to learn how to apply slope to things that we have not applied slope to before. Maybe a quadratic function, maybe a cubic function. But before we get there, let's look at some other functions that we should be familiar with. So beyond our polynomials, we've learned some trigonometric functions. A lot of people get into intro calculus and they really don't know if trigonometry is really going to translate into this intro class. They learn trigonometry in high school and they don't really know, they don't hear from people that, oh, you need to know a lot of trig. There is some amount of trigonometry. Not so much triangles everywhere and understanding to use sine and cos of triangles, but instead the actual visual of the functions themselves. So if you'll recall, we do know what sine, cos, tan, what they look like when they are graphed as functions. We've got this, which would be the cosine graph. This is y equals cos x. And that, of course, is if I properly label my graph with y and x. You can use any variables if they're appropriate. Sometimes you'll see s is equal to cos t or whatever else. But here, x and y are common. We'll use y and x. That's what y equals cos x looks like. Y equals sine x is going to look something like this. So that would be your y equals sine x graph. Those are kind of the two basic ones, but we've learned a little bit more than that. We also know what the tangent is. And I'll just use a little bit of room in the corner here before I erase everything and we start fresh. Y equals the tangent of x. We've seen that graph before as well. And it takes a very interesting form as it just looks like an endless series of these shooting off to infinity small subgraphs. And that's exactly what they are. Now, you may recall why that is. We'll do a brief refresher. Why is y equals tan x constantly going up and down to positive and negative infinity? Well, it's because tangent of x is known to be equal to sine x divided by cos x. Now, sine x divided by cos x you should be able to graph it. There should be no problems there. But there are points where this is going to be problematic. We have one taboo in math that keeps popping up over and over, and it is division by 0. So if I were to plug in any x value such that the cosine gives me 0, let's look at my cosine graph. There are a number of instances where I can plug in a value such that it will give me a 0 output, a 0 y value. That will be a big problem. Division by 0 simply cannot happen. So what you'll notice is that these points, these zeros on the cosine curve, translate perfectly to these spots where there in fact is no graph for the tangent. It simply can't exist. Instead, it will just approach infinity. Because if you divide by impossibly small numbers, you are actually creating impossibly large numbers. Our final type of graph that you may be familiar with is an exponential graph. So these are graphs that take the form y is equal to a raised to the power of x, where a is a real number. So you may have seen y is equal to 2 to the x. And you may have learned in a previous course, well, how to graph that. And you can get a bit of an understanding just by plotting a couple points. If I plug in x is equal to 0, I would get y is equal to 1. If I were to plug in x is equal to 1, and again, of course, always labeling your x and y. If I were to plug in x is equal to 1, I would get y is equal to 2. And then if I were to plug in x is equal to 2, I would get y is equal to 4. So it's actually growing quite quickly. And that's the thing about an exponential graph. It grows very quickly. So this is our final type of graph that we should, at least to some extent, be familiar with up to this point. We've looked at trigonometric, exponential, and then our polynomials, maybe the most common ones. There's also inverse trig, and inverse trig will actually probably pop up in this course, but we will not focus too much on the inverse trig just right now. So the idea being, if I visualize an exponential graph, or maybe a trigonometric graph, maybe the sine curve, or maybe some sort of polynomial, this would be maybe a 5th or 6th degree polynomial with all of those curves going on in there. One thing that is common is there's no slopes. We don't talk about m values. There's no slopes going on here. So what are we talking about when we mention these rates of change? How can I apply a slope to these ideas? And that's exactly where we're going to go here. So we are going to go back to the example of throwing the ball in the air. So imagine I throw a ball in the air, it reaches a height, and then it comes back down. I want to ask some questions about the flight of that ball. So let's get some details here so that we can actually perform some calculations. In this case, we are going to use different axes. The only reason you would ever rename the axes is if it makes it more clear. And we're going to call these T and S, where T measures time. S tends to measure position. So that's what we're going to measure. S is time and S is position. Now, position is a very broad term that can be used in physics and in mathematics, but here it's quite clearly measuring height. So we can be more specific than position and clarify that this, what we would call the y-axis, what is now the s-axis, it's measuring height. It's the height of the ball. So if I know that the t-axis is measuring time and the s-axis is measuring height, I now need a function. What is this actual function? It is s of t is equal to negative t squared plus 4t plus 2. Now, as soon as you're given that function, you can graph it. Now, we've learned all sorts of different ways of graphing these things. You can start with your old negative b over 2a. We remember that. X is equal to negative b over 2a is going to tell you exactly where that vertex is. But of course, I've made a small mistake because these are s's and t's. We are not talking about y's and x's. So this would instead be measured as t is equal to negative b over 2a. And that will work brilliantly for you. You will figure out exactly where that vertex is. But sometimes when the numbers are small, it's just simple enough to calculate. So let's plug in t equals 0. There's not much work necessary here. Negative 0 plus 4 times 0 plus 2. That immediately tells me that this point right here is t equals 0, s equals 2. I plug in t equals 0, and what the function gives me is that s is equal to 2. Now I keep plugging in values, and again, they're small enough, and this equation is simple enough that I really can just do these in my head with some mental math. If I plug in 1, t is equal to 1, I get negative 1 plus 4 plus 2 gives me 5. So this value right here is going to be 1, 5. When I plug in t is equal to 1, s is equal to 5. We keep doing this. We plug in 2 and 3 and 4. We get that 2 pairs up with 6, and we get that 3 actually pairs up with 5. Now, I could go through the negative b over 2a, and in fact I will. Let's go for it. So negative b over 2a says that t is equal to negative, that's my b term right there. If I were to write this as at squared plus bt plus 2, then b is that 4 there. So negative 4 divided by 2 times negative 1, because negative 1 is the a term, I will be left with 2. That's negative 4 divided by negative 2 gives me positive 2. That tells me exactly where this axis is, exactly where I will find that maximum value. But, as you may have recognized, there are other ways of doing this. When I started plotting these values, I recognized that 1, 5 and 3, 5, they have the same height. And there's a really neat thing about quadratic equations. When you find two x values, or t values in this instance, that have the same height, then if you go exactly in the middle of those two, That is your axis of symmetry. That is your vertex. That is the peak that we are looking for. So negative b over 2a does the trick. This, we just kind of stumbled on the answer by recognizing that symmetry trick. So just kind of refreshing all of these old things that we've learned in grades 10, 11, 12. We've now got this thing mapped, and I could ask some questions. So at what height is the ball at time t equals 0? That's easy enough to answer because I've plotted some of the important points here. So when t is equal to 0, the height is 2. 2 somethings. The question specifies that s is measured in meters. If you have taken some physics courses, you will get that the units are so very important. We always talk about meters and seconds and meters per second. Maybe in your pure math courses you haven't come across this very much, but it is a very good habit to get into of recognizing what are the units that we're measuring here. So the position, the height, it's being measured in meters, and the time is being measured in seconds. That's of course very reasonable. If you throw a ball in the air, it's not going to take days or hours to come down. So seconds seems quite reasonable here. So the questions, they could say something like, when t is equal to 0, what is s equal to? That is as simple as plugging in t equals 0. When t is equal to 2, when t is equal to 3? Well, we've already answered these questions. The height is 6 meters above the ground, 5 meters above the ground, and so on. At what time does the ball touch the ground? Okay, this should bring back some memories. Let's just move this out of the way and move this over. I want to know what this value is, what these coordinates are. Now, one of them is easy. The s coordinate's 0. The height is 0. It's when it touches the ground. But what is the t value? At what time does it touch the ground? So let's consider what the question's asking. I want to know when the function is equal to 0. So I have an equation that I can build here. 0 is equal to negative t squared plus 4t plus 2. This should immediately bring back ideas of factoring to solve, but also the quadratic formula. You'll notice that there is no brilliant way to factor this, so that we will get the answers very quickly. Instead, quadratic formula is going to come out here. And we do need to be very acquainted with our quadratic formula. So that states that t is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So t is equal to negative b. Remember that this takes the form at squared plus bt plus c. So I know that negative b is in fact negative 4 plus or minus the square root of 4 squared minus 4 times a, which is negative 1, times c, which is 2. We divide this by 2 times a. A is equal to negative 1. So we're going to go through this step by step. You won't always necessarily have a calculator at the ready, so you do need to be prepared to be able to actually calculate this step by step. So negative 4 plus or minus, let's see what's actually going on under this square root. 4 squared is 16. Negative 4 times negative 1 times 2. Well, negative 4 times negative 1 is positive 4. Multiply that by 2, and you get 8. So this becomes 16 plus 8. Very common mistake would be to put 16 minus 8. But recognize, 2 negative signs here are canceling out to make a positive. We're going to divide all of this by negative 2. So we're going to move now to another board and just keep simplifying. So t is equal to negative 4 plus or minus the square root of 24 divided by negative 2. Now, whenever you see a plus or a minus sign on a fraction, that means you can bust it apart into 2 separate fractions. So let's visualize this as negative 4 divided by negative 2 plus or minus the square root of 24 divided by negative 2. And now we've taken this larger, uglier looking question and broken it into two smaller pieces that we may be able to actually solve. So now t is equal to, what is negative 4 divided by negative 2? Well, 4 divided by 2 is 2, and the negatives are actually canceling here. So while it may have been a very common mistake to get negative 2 there, it is in fact positive 2. Because the negatives are canceling and 4 divided by 2 is 2. So we got 2 here, nice and simple. But this appears that it's going to be a little bit more messy. So it's 2 plus or minus something. What is the square root of 24 business? Well, the square root of 24 is equal to the square root of 4 times 6. That's what 24 is equal to. We're dividing by negative 2. And we'll keep writing. You'll notice we're showing a lot of steps, and it is a very good practice to get into to show a lot of steps. First off, if you do something wrong, the markers can give you partial points. But also, if you show every individual step, and you catch yourself making a mistake, you can go back and figure out exactly where you made that mistake. So here, we're just going to keep moving along. We've got positive 2 plus or minus. The square root of 4 times 6. Well, we recognize our rules of square roots that we have learned previously. This is the square root of 4 times the square root of 6. That's a rule. You can take that multiplication sign and you can actually bust it apart as 2 separate square roots divided by negative 2. Now, why have we done any of this? Is it actually simplifying things? It actually looks like it's making things messier. But it's because we know what the square root of 4 is. Square root of 4 is 2. So t is equal to 2 plus or minus 2 times the square root of 6 divided by negative 2. Now, that 2 and that negative 2, they're going to cancel out very nicely. So t is equal to 2 plus or minus 2 divided by negative 2 is just negative 1. So we've just got negative 1 times the square root of 6. And now this is vastly simpler than maybe what we had up here at the top, where things are actually looking pretty large and bulky. We've got it broken down into just 2 pieces here. 2 plus or minus negative square root of 6. Now, we're not quite done. I'm going to move this board over and erase our old work with the axis of symmetry. And we're going to keep working with this thing. So t is equal to 2 plus or minus negative the square root of 6. There's something weird going on with this plus or minus and minus business. So I'm already accounting for both the positive and the negative. So that negative sign, it doesn't matter. You multiply it through by plus or minus, it gives you plus or minus. So we are left with 2 plus or minus the square root of 6. This is as far as we can simplify it. We could factor 6 as 2 times 3, but neither of those are well-known square roots. So we are left with 2 plus or minus the square root of 6. In a lot of cases, this will be the answer that you are expected to provide because you need to give that exact answer. That answer that shows I didn't just plug in the square root of 24 into my calculator and write down the answer. You really do need to show that you can simplify to the best of your ability down to something like this. So this will probably be the answer it's looking for, but when it comes to actually mapping the thing onto the graph, which is now covered up, I want to know that value. And that value is going to make a lot more sense if it has an estimated value with a decimal point in it than just 2 plus or minus the square root of 6. So it's at this point, now that we have our exact answer, that we are now comfortable going to the calculator. Because the square root of 6 is not something you are expected to memorize. So the square root of 6 is equal to roughly 2.45. So we're comfortable saying t is roughly equal to, that shows that I am doing some rounding here, 2 plus or minus 2.5. So t is roughly equal to 4.5. And I can now say, I'll put 4.5 there, it's roughly correct. It's closer to 4.449 and so on. But you don't have room to put infinitely many decimal places, so we'll round it to 1 for now. You may have instances where a specific instructor may say 2 decimal places, 4 decimal places, or any certain number. So be prepared to round as appropriate, understanding that values less than 5 round down, values 5 or greater round up. But in this instance, when we were given something that looked like 4.49 whatever, we know that we can round that up to 4.5. Okay. Up to this point, honestly, everything's been reviewed. Hopefully you're comfortable with everything we've done up to this point, because these things will be expected of you. But now we're going to get into something new, because I'm going to ask, if I get my page, a new type of question, which is to say, at what velocity is the ball moving at time t equals 1? I'm going to take another moment to erase all the boards. So velocity may be a fairly new word. Speed is an appropriate way to refer to it. So velocity is pretty much the same thing as saying speed. And let's go back to our units. So t, the time, it's measured in seconds. As we go across this t-axis, we are measuring in seconds. The position, the height, it's being measured in meters. We were told this stuff in the question. No assumptions necessary. Velocity was not mentioned. We were not told anything in the question about what the velocity is or how to measure it. But there is a standard. Velocity, or speed, is measured in meters per second. Or if you were given the question in feet and minutes, then you would measure it in feet per minute. But we feel good measuring it in meters per second because those are the units we were provided. S measured in meters and t measured in seconds. Now, we've never had to do anything like this before. When we're given a quadratic function, we are just asking very basic questions. What is this point? What is that point? What is the maximum? What is the minimum? Maybe when it hits the ground. Those are the simple types of questions we've been asking. The speed is something new. Let's consider what speed even is. Well, there is a formula to calculate the meters per second. Let's consider what would happen if I wanted to measure the average velocity between 1 second and 3 seconds. What is the average velocity between 1 second and 3 seconds? So let's go to our actual graph here. We've got t is equal to 1 and t is equal to 3. We know that the ball is moving. The ball is going up and coming down at that point. I want to know the average velocity between t equals 1 and t equals 3. How fast is that ball moving between those points? The problem is it keeps changing its speed. It's going faster and then it's going slower. You can picture this as you throw a ball in the air. It starts going very quickly, and then as it reaches its apex, it starts to slow down until it starts to come down. So the problem is the speed is constantly changing. The velocity is constantly changing. At some point, it even changes direction. It starts going up, and then it changes direction and starts coming down. So measuring this velocity is starting to seem very tricky. How are we going to actually approach this? Well, one way to do it is to measure the average velocity. This we are very capable of doing. We can measure the average velocity. It is as easy as taking the position, which is s of 3 minus s of 1, and dividing it by the difference in time, 3 minus 1. Let's consider why this makes sense and what we're actually doing here. The velocity is measuring how fast something changes. Velocity. How fast something changes. Consider the slope, which we talked about before for our linear functions. It is rise over run, how steep the function actually is, how fast the function grows, or how fast the function changes. When I alter my question here, and instead of talking about position, at what point does it touch the ground, at what point is it at its apex, and I start saying things like, how fast is it changing, I have changed my perspective from t and s to speed, to rates of change, to slopes. So, I'm now trying to calculate a slope where there are no slopes. Let's consider, I'll use a blank board here, if I am looking at a quadratic function and I try to calculate the slope is ever changing. At this point, the slope looks very steep. But at this point, the slope is not steep at all. It's ever changing. It is positive, then it goes negative. There is always a different slope. Starts very steep, gets less steep, less steep, less steep, and then it starts getting very steep in the opposite direction. How can I measure a slope that is ever changing? Well, one thing that we could do is draw what's known as a secant line. If I have a quadratic equation, a quadratic visual here, a graph, and I want to know something about this point, I want to know its slope, one thing I could do is measure the slope of a secant line. That's an easy line to draw because all you need is 2 points to draw a secant line. And you can measure the slope just like we would with a linear function. So if I go back to this equation that I wrote down as the average velocity equation, maybe it will ring a bell as being the delta y divided by delta x, or also known as the y2 minus y1 divided by x2 minus x1 equation for slope. I am actually calculating an m value. I am calculating a slope. What slope am I calculating when I ask for the average velocity between 1 and 3 seconds? I am asking for the slope of the line that goes through 1 and 3. The line that goes through 1 and 3 does not look very useful. It has a slope of 0. It's visual. We can see that it has a slope of 0. It neither rises nor falls. Its rise over run would clearly show no slope. But we can actually show this with numbers, so let's do that. Because I can very much calculate s of 3 minus s of 1 divided by 3 minus 1. S of 3 minus s of 1 divided by 3 minus 1 is equal to s of 3. What happens when I plug in 3 to this function? I get 5. Then I subtract s of 1. S of 1 is 5. Divide that by 2. I get 0 over 2, which is 0. If my desire was actually to figure out how fast this ball is moving, and I just calculated that it's not moving at all, something has gone terribly wrong. So what I'm going to do is I'm going to say, this secant line is not very useful. What secant line might be more useful? So again, let's go back to what the original question was, because we're a couple layers thick here. So let's remember what we were actually asked. The initial problem as written is, what is the ball's velocity at t equals 1? Now, I don't know what to do at t equals 1, because consider what would happen if I actually tried to use the slope formula at t equals 1. Remember that m is equal to y2 minus y1 divided by x2 minus x1. If I only have 1 point, there's a problem here. Because I can't just plug in 1 for both of these values. Something terrible is going to happen I'm going to be dividing by 0. Again, we're breaking that rule of mathematics that you can't divide by 0. So I can't just plug in t equals 1. So I tried something. I plugged in another value. I plugged in 3 as well. I said, well, if I can't figure out exactly at 1, let's figure out the average between 3 and 1. And I get a useless answer. So let's try something else. Instead of drawing the line that goes from 1 to 3, let's draw the secant line that goes from 1 to 2. So that is the unique line that goes through 1, 5, and 2, 6. I'm going to use the exact same formula. Push this all the way over. M is equal to y2, which is this s value, 6, minus y1, which is this s value, 5, divided by x2 minus x1, which is 2 minus 1. I'm now getting, at least not division by 0, I'm getting 1 divided by 1. 1 meter per second. This is odd. I calculated the average velocity for this secant line and I got 0 meters per second. Now I calculate the average velocity for this line and I get 1 meter per second. But these are all just estimations. I wanted to use this formula. I don't want to plug in a second value. I don't want to plug in t is equal to 2, t is equal to 3, because that's just an estimation. That's just an average. I want to know the velocity at t equals 1. Not an average from 1 to 2 or an average from 1 to 3. I want to know exactly at t equals 1. So what we're going to do is what's called a limit. We are going to start with values far away from 1. But we're going to notice a trend as we calculate values closer and closer to 1. So the next one I'm going to calculate is one that is much closer to 1. Let's calculate the average s of 1.1 minus s of 1 divided by 1.1 minus 1. I can't actually get my perfect instantaneous velocity, my velocity at exactly that instant, 1 second, but I can get really close. I started at 3, and then I went down to 2, and now I'm going to go to 1.1. And after this, I'm going to go to 1.01. And while I know I can never actually get to 1, I can plug in values that are really close to 1. And I'm going to notice a trend. I'm going to notice what we will come to call a limit. So here, let's actually plug the numbers in. We need to actually do these calculations. Plugging 1.1 into this formula, I will push the board over so we can get a visual on that formula again. S of t is equal to negative t squared plus 4t plus 2. I do have to plug in that number 1.1. That's a little bit of work, and it's not something you'll be expected to do in your head. So it's negative 1.1 squared plus 4 times 1.1 plus 2. Now, I'm running out of room on the board here, and I still need to subtract s of 1, but I've calculated s of 1 enough times. I know it's 5. So I'm going to subtract 5. We're going to divide that by 1.1 minus 1. Well, when you plug that into a calculator, which again is fine, you're not expected to do all of these calculations in your head, negative 1.1 squared plus 4 times 1.1 plus 2 should give you 5.19. So we get 5.19 minus 5 divided by 0.1. Now, again, not expected to do that in your head. You can calculate this using a calculator. .1 minus 5 divided by 0.1 is going to give you the answer 1.9. So let's consider a table. Let's build a table of all of our answers that we've gotten so far. So I'm building a velocity table. I'm going to take the average velocity from 1 to 3 seconds, the average velocity from 1 to 2 seconds, the average velocity from 1 to 1.1 seconds. Let's see what happens when I plug these values in. I get 0. That was a weird one. Why was it 0? We'll get to that later. Then I got 1, and then I got 1.9. Looks like the numbers are getting slightly more exact, but we need far more evidence before we can conclude anything here. So let's see what happens as I go from 1 to 1.01. Well, exactly the same as you did before, you're just going to plug in 1.01 instead of 1.1. So my slope is 1.01 minus s of 1 just s of 1, divided by 1.01 minus 1. Now, that should give you, if we do our calculations correctly, 5.0199 minus 5 divided by 0.01. Now, again, not a fun calculation to do by hand, but you can plug that into your calculator, and you will get 1.99. It's starting to become clear what we're approaching, but we'll do one more. I want to know the average velocity from 1 to 1.001 seconds. I will spare you the work. If you do go through the steps, you will get 1.999. Let's get a visual again, just to make sure we understand what we've done here. I'll draw that better. I have a parabola, and I started with an unhelpful value. This completely sideways straight line, which did me no good. So I started bringing my values closer and closer to t equals 1. I looked first at this line, and then maybe this line, and then the values got so close that I can't even really draw them distinctly on this graph. But as you keep changing where that second point is, the line changes ever so slightly. They get steeper or they get less steep. In this case, they're getting slightly steeper every time you move closer to 1. In the end, we're actually just measuring the slope of the line that only touches 1. Now, the way that we reach that, because again, the formula fails us. We would try to do the formula for this line, the line that only touches the graph at one spot, that nice spot that we like, t equals 1. If I tried to calculate that, I get a big problem because the slope formula requires 2 different values. I only have 1. I've only got t equals 1. When you try to plug that in for both values, you get division by 0. So that method just doesn't work. It's this alternative that gets us there, where we keep plugging in closer and closer t values until we realize that there is a pattern. And in this case, the pattern is clear. What we call the limit is equal to 2, clearly. So without actually measuring the slope of this line, because again, I do not have enough information to measure the slope of this line, because to measure the slope of that line, I need to have 2 points on it. My formula for slope requires 2 points on that line. Don't have them. I try to plug 1 point in both times, division by 0, it fails. Without actually calculating the slope of that line, I calculated it by taking a limit of all the lines as they get closer and closer to that value. Every one of these lines are referred to as secant lines. Secant meaning touching the graph in 2 places. The limit of these secant lines, as they get closer and closer to the actual point I'm interested in, that has a name. It is called the tangent line. Something that your professor may or may not get into this semester is exactly how these words, the secant line and the tangent line, relate to the trigonometric ideas of a secant and a tangent that can be applied to a value x. The limit that we just looked at is actually quite unique to calculus. It's very useful in calculus. It's not the simplest form of a limit, though. Now that we have an understanding of what a limit is, something that you approach, you get closer and closer and closer to, but maybe you never actually reach, we can actually view this in things that we're much more familiar with. If I were to draw a cubic function, and instead of getting the secant lines and the tangent lines out, I wasn't talking about instantaneous velocity. Very important idea for calculus, rates of change, how fast things are moving. But if we step back and ask a much simpler question about limits, and I just say, what is the limit if I call these x and y? What is the limit as x approaches this value? So let's give these some values here. Let's give them some numbers. I'll give these some names. This one will be called a. So there's a way of writing this. If this function is called f of x, I would write my question as, what is the limit, I'm using some script here, which is somewhat common in writing down limits, LIM, short for limit. What is the limit as x approaches a of f of x? This is the way you may see a question written. So it took some work last time. I had to get values that get closer and closer and closer to the value. But here, it seems quite obvious. If I put some actual numbers on this curve, the value is just 3. F of x is equal to 3. It's clear. We have learned how to plug values into a graph. We can see it. F of x is equal to 3. If I draw roughly a horizontal line there. The graph as it approaches from the left, sure looks like it's approaching 3. As it approaches from the right, it sure looks like it's approaching 3. This answer is clearly 3. The answer is 3. But now why are some limit questions easy and some questions actually quite difficult and take some work, like we did with the last one, talking about instantaneous velocity? And it's because some graphs are what we call continuous and some graphs are not continuous. Now, continuity is something we won't quite get into with this video. That will be done with your professor in the lectures. But we can get a very surface level understanding of continuity. And it's going to feel very usual to us because these are the graphs that we've seen before. We have seen polynomials, trigonometric, and exponential. And almost entirely throughout every one of these types of graphs, you will see continuity throughout. Continuity at its most basic idea is you can draw the graph without lifting your pencil. It doesn't jump around. And that's our basic idea of a graph. We view the sine graph. We view a cubic graph. We think about maybe an exponential graph. They're all drawn very quickly without raising your pencil, so to speak. You can draw it in one motion. But there are some that we look at that aren't. Let's think about tangent again. Y is equal to the tangent of x. Well, we remember that is kind of a funny looking one. Something like that. Well, in y is equal to tangent of x, you are getting that some spots are beautiful and continuous. If I asked, what is the limit as x approaches this value? Well, clearly, as I approach from the left, it looks like it's approaching 0. And as I approach from the right, it looks like it's approaching 0. So the answer is clearly 0. There's no question that the function is approaching 0. But now I'm going to start asking, what is the function approaching as it approaches this line right here? Well, now it's less clear because I had to lift my pencil, so to speak. From the left, it's just going up and up and up and up. It looks like it's approaching infinity. From the right, it's just going down and down and down and down. It looks like it's approaching negative infinity. It's not approaching the same thing from both sides. One side's going up, the other side's going down. They're not meeting in the middle. in the same way that they were here at this point. So at this point, we would say that this limit does not exist. So let's be clear about what such a value might be. Y is equal to tangent of x is the same as y is equal to sine x divided by cos x. Now, you reach these problem areas, we discussed this already, every time you're dividing by 0. So when is cos of x equal to 0? Well, there are infinitely many places where cos of x is equal to 0, but one of them is at pi over 2. Let's do a brief view at our unit circle. I advise if your unit circle is weak, please study up on the unit circle. It really gets to be something that is implied in a lot of questions, that you have a competence in working with the unit circle. So here, if someone asks you, in the tangent graph, when are you dividing by 0? When does that function not exist? Well, we need to know when cos of x is equal to 0. If I visualize my unit circle, I understand that cosine is the x-axis, or the x value would be even better to say, the x value. So as I rotate around this circle, the x-coordinate is the cosine value. So if I want to know when I am at cos equal to 0, it would be any time that x is equal to 0. There are 2 points here. So remember, with the unit circle, we tend to measure theta, that's our degree. So when that degree is pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, and so on, you know, infinitely many values, that's when you're going to have cosine equal to 0. Because cosine is always measuring the x-coordinate when x is equal to 0. All the way out here, x is equal to 1, maybe here, x is equal to 1/2, but here is where x is equal to 0. There are exactly 2 points on that unit circle. So let's go to x equals pi over 2. That's going to be right here. If I asked, let's make this very formal, what is the limit as x approaches pi over 2 of the function tangent of x? If I were to ask you that question, you would probably, using the tools we've learned up to this point, you'd probably start by drawing the graph. You would look on the left, you would look on the right. So let's go to x equals pi over 2. That's right here. X equals pi over 2. And we can see, uh-oh, there's a problem. It's this weird dashed line that I've written to show that this side's going up and up and up and up, and this side's going down and down and down and down. Clearly, that limit does not exist. There is no single point that you can point out and say, the function is approaching that. So this limit does not exist. When you're writing your answers to your professor, often you will write does not exist. Sometimes they will even instruct you to just write DNE as a shorthand, but it doesn't exist. There's no answer. You can't say it's 1, it's 0. You shouldn't even say it's infinity. It does not exist. So we've looked at the idea of limits existing. That's where the function does everything you would expect it to do. And again, I'd like to reiterate, this is basically everything we've ever learned. If I look again at that sine curve, this thing is continuous. You can draw a sine curve without ever actually lifting your pencil. So you can tell that at any individual point, even if it's not a point that we calculate much, if I ask you something about 12 pi over 5, if x is equal to 12 pi over 5, what's going on there? Well, you're just going to say, without any extra work, I didn't have to lift my pencil. Clearly from the left and from the right, they're approaching that same y value. And that means that that limit exists and it is equal to that value. We've seen the example where this fails, where I try to approach from the left and the right, pi over 2 in this tangent example. But the problem is they're going in different directions. One's going to infinity, the other's going to negative infinity. This is an instance where the limit does not exist. Now we're going to introduce a fourth type of function. So we've got our polynomials, our trigonometric, our exponential, There's a new one that we're going to learn in this class, and it's called piecewise. A piecewise function is where you basically take a lot of functions and just stitch them together. So let's make a little bit of room and see what can go right and what can go wrong with a piecewise function. A piecewise function is always written using this large bracket notation. Well, I say always, usually. And it's written in the form where you have a list of functions. So let's say that my graph follows f of x is equal to x from negative infinity all the way up to negative 3. Then maybe it's just equal to negative 3 less than x up to 4. And then from there, maybe it's equal to x over 2 from 4 to infinity. Now, it doesn't look like it, but this is one function. We've just taken all these smaller functions and stitched them together to create a single function. And you can graph it. You really don't need any extra expertise to graph this thing. As I go from negative infinity, so that's all the way off the page on the left here, as I go from negative infinity all the way up to negative 3, let's plot some numbers in here. Negative 1, negative 2, negative 3, negative 4, negative 5. From off the page here all the way up to negative 3, it's just following the function x. Well, negative 4, negative 4, negative 3, negative 3, negative 5, negative 5. You can see it is just that y equals x line. So I have made a small mistake here because, as you can see, I have not defined what this function is at negative 3. As long as it's less than negative 3, it's x. And as long as it's greater than negative 3, it's negative 3. But I don't actually have what it is at negative 3. So what will be very common is an equal sign in there. We've got less than or equal to negative 3. And then here I'll put less than or equal to positive 4, just to make sure it's defined at every value. Now, we've got our first bit of the function. From all the way off the page up to negative 3, I've got that it is following y is equal to x. Now, as we go from negative 3 up to 4, let's plot some x values here. 1, 2, 3, 4. We are now going to do negative 3 to 4 is just the constant function negative 3. So it's just going to be negative 3. Now, I can see that I've messed up my scale a little bit, so I'll fix that. So we are building a function by stitching together other functions. It started with y equals x. Then as soon as you got to negative 3, it turned around and it became a new function, the constant function negative 3. And now, from 4 onward, it is x over 2. So let's think about this. X over 2, well, it's positive. It has a slope of 1/2. We know these things. X is equal to 4. That means y is equal to, if x is equal to 4, that implies y is equal to 4 over 2, which is equal to 2. Well, that's weird. We haven't had a positive value yet. So we jump all the way up here. So we ended here. We had no further to go. We can put a little circle there. We stopped. No further to go. When we plug in this 4 here, we're now just going to keep going with x over 2, which is, as you can visualize, a positive slope, but not a very steep one, because the slope is only 1/2. So this function has now gotten to look quite odd. It started out making some sense. I had a nice linear function that then became a constant function. Then it just became a linear function again, but it didn't meet me at the same spot. It jumped. And that is exactly what this is called. It's called a jump. At x equals 4, there is a jump. That is a perfectly scientific, appropriate way to write down what happened in that graph. At x equals 4, there is a jump. I could ask the question, what is the limit as x approaches negative 3 of f of x? You're going to have questions that are going to look very familiar, very similar to this. So I'm going to track down negative 3, and I'm going to approach negative 3 from the left and from the right. And I'm just going to try to argue that this graph is approaching that value. From the left, I move along this straight line, and I can see what I'm approaching. From the right, I move along this line, and I see what I'm approaching. In both instances, they are clearly approaching the same value. Y is equal to negative 3. So the limit as x approaches negative 3 is y equals negative 3. But now I could ask a similar question at another point in this graph. The limit of f of x as x approaches 4. As I approach 4 from the left, moving along on this constant function, I'm getting close to 4. The value I'm approaching is negative 3. But as I move to the right, or to the left that is, the value that I'm approaching is 2. These two values disagree. So we say this limit does not exist. There is no value that we are approaching from both the left and the right. The function can't seem to agree. So we say the limit does not exist. Now, I will clarify, if I were instead asking about x equals 3, the limit as x approaches 3 of f of x, what is that equal to? Well, let's erase some of these lines and try again, see what we were doing. As I approach 3 from the left, well, I'm clearly approaching negative 3. As I approach it from the right, I don't have to worry about this line anymore. That's far away. I have closer values. And the closer values make everything make good sense. Everything looks continuous. I can draw that line without lifting my pencil. So the limit as x approaches 3 is negative 3. Because as x approaches 3 from the left and from the right, it is approaching the same value. Y is equal to negative 3. So that limit exists, while the limit as x approaches 4 does not exist. Okay, one last thing we're going to introduce is, if this limit does not exist, what can I say? How can I document what I've learned about this thing? Well, we have new words. We can now say the limit as x approaches 4 of f of x, that doesn't exist, but we're going to define something new. The limit as x approaches 4 from the negative side. That is to say, approaching from the left. We're coming from the negative side over to 4. In the same way, we can talk about the limit as x approaches 4 from the right, from the positive side. These things can be measured because they don't need things to agree anymore. Let's look at the limit as x approaches 4 from the negative side. Okay, here I am coming from the negative side, and I'm getting closer and closer to 4. As I approach 4, I am clearly approaching the value y equals negative 3. So the limit as x approaches 4 from the negative is negative 3. Now, what is the limit as x approaches 4 from the positive, from the right? As I approach from the right, I am following this line, trying to find 4. I get closer and closer to x equals 4, and as I approach, I am clearly approaching this line, this dot that appears at x equals 4, y equals 2. So the two limits, the left side limit and the right side limit, both exist. They're approaching values, but they're not approaching the same value. So we say that they exist, but since they don't agree, this limit does not exist. So now you may be wondering, well, how would the limit as x approaches some value a from the left of f of x, how would that not exist? Clearly that will always exist, right? Well, the only way it could not exist is if we were not approaching a number from the left. And this brings us back to that tangent graph. if we visualize that tangent graph and we ask for pi over 2, what is the limit as x approaches pi over 2 from the left, from the negative side? Well, I'm going to approach pi over 2 from the negative side. I just keep going higher and higher and higher. There is no point that I'm approaching. I'm approaching infinity. Well, you don't technically say the limit is infinity. You say that the limit does not exist. There may come points where you'll actually want to know, does it approach infinity or does it approach negative infinity? But from a technical standpoint, in both of those instances, the limit does not exist because it does not approach a real number. Now that we have an idea of what a limit is, we've actually got some algebraic ways that we can write these and actually some laws, what are called limit laws, that we can work with. So, if I have two limits, the limit as x approaches some value a of a function f of x, and I also have the limit as x approaches a of another function g of x, there are actually a lot of things that I can state that may help me calculate some things about these. So I have that the limit as x approaches a of the sum of these two functions is equal to the sum of the individual limits. This can be summarized as, and this will be a very simple thing, or a very important thing, I think, to memorize, is the limit of the sum is equal to the sum of the limits. Now, we get some very similar results, starting off with the difference. The limit of the difference is equal to the difference of the limits. This third one is talking about scalar multiples. Now that word scalar multiple, it's a real number. So if c is any real number, and don't just think of these in abstract terms, you can actually think about these with functions. So if f of x is, say, cos x, and c is 12, I'm not looking at the function cos x, I'm looking at the function 12 times cos x. Well, calculating that limit, not that hard, because the limit at any value when I'm dealing with cos x, I'm just going to multiply it by 12. The idea being that scalar multiple can be factored outside of this whole limit business. So it makes it easier to calculate. I don't need to factor in this 12 until the very end. Calculate the limit and then multiply it by 12 to make life easier. Okay, we've got a few more rules. This says that the limit as x approaches a of the product, f times g, multiplying two functions together. This is a very neat rule that it tells us it is simply the product of the limits. So the difference of the limits is the limit of the differences. The product of the limits is the limit of the products. And the sum of the limits is the limit of the sums. And then finally, what's the fourth one? Division. It is roughly going to follow the same rule. The limit as x approaches a of f of x divided by g of x, dividing functions by each other, not something we do very often, but it will become very useful in this class for us, is just the division of the limits. But this one has a caveat. Because, of course, anywhere there is division, you have to watch out for division by 0. So there is a comma. If the limit as x approaches a of g of x is not equal to 0. That's the only time that's going to hold. If it is equal to 0, then I would be making a claim that something is equal to dividing by 0. But you can't divide by 0. So that's the only time it fails, though. So in general, always holds as long as that denominator is not equal to 0. So we're going to finish this off with a little bit of practice. And we're going to look at a couple of examples here. And in these examples, we're going to be looking at what are called rational functions. A rational function being what you get when you take a polynomial and divide it by another polynomial. So that's exactly what this is, a polynomial divided by another polynomial. But there's not going to be any problem here. It's a polynomial divided by another polynomial. We know what polynomials look like. They're these nice curves that you can draw without lifting your pen. So why would there be any problems? We've gone through examples where there were problems. Y equals tan x. Yeah, sometimes the limit doesn't exist there. Piecewise functions, sometimes the limit doesn't exist there. But what could possibly go wrong here? Well, it'd be division by 0. The same thing that happens with tangent x. When you divide by that cos x equals 0, you have problems, infinities, things ruining your limits. Well here, if that were equal to 0, I'd be in trouble. If this were trying to measure the limit as x approaches -1, because -1 would make that a 0 denominator, I would have problems. But it's not. Just asking the limit as x approaches 2. So since we're just looking for the limit as x approaches 2, this is just 2 squared plus 2 divided by 2 plus 1 is equal to 6 divided by 3, which is equal to 2. Easy peasy. The limit as x approaches 2 is equal to 2. Now let's look at what happens when it does get messy. If I want the limit as x approaches -2 of x squared minus 4 divided by x plus 2. We have a problem. If I try to plug in -2 here, I get 0 over 0. That's a problem, because we can't divide by 0. So something is wrong. I may want to jump straight to the end and say, this limit does not exist. But I can't do that, because there is an algebraic trick that is going to help us here. We know that this can be recognized as a difference of squares. This numerator, x squared minus 4, it's actually equal to x minus 2 times x plus 2, using our difference of square factorization. Now I see what's going on and why there is actually an answer to this, because I can cancel out like terms in the numerator and denominator. So this thing is actually equal to the limit as x approaches -2 of x minus 2. Well, if I plug -2 into that, I get an answer, -4. So getting that 0 denominator is not always the end of the road. If we were to visualize this graph, we would see that even though it looked messy, x squared minus 4 divided by x plus 2, the graph itself was just the x minus 2 graph, which is that. So sometimes when you get this division by 0, you will have to look for extra steps just to make sure you're not making an unnecessary assumption about that limit not existing. Because in this case, it does. The limit exists, and it's equal to -4. When I plug in -2, from both sides, it approaches -4. Okay, and our last example is going to be the limit as x approaches 2 of x minus 2 divided by x squared minus 5x plus 6. Now, naively, I can just start by plugging in 2. Maybe I can plug in 2 and everything will be great. I get 2 minus 2 divided by 2 squared minus 5 times 2 plus 6 Well, the numerator is clearly 0, 2 minus 2. The denominator, I get 4 minus 10 plus 6, that is 0. Okay, I've got another 0 over 0 state. I'm not going to jump straight to there's no possible way to answer this. I'm going to think about which algebraic tricks, what I can apply to this to actually simplify it. And it's going to be factorizing that denominator. I recognize that as a quadratic that can be factorized. And it's not going to require some difficult quadratic formula or anything like that. I know how to figure this out. I just want to find the two values that add to give me -5 and multiply to give me 6. So I can rewrite this as the limit as x approaches 2 of x minus 2 divided by what two numbers do add to give me -5 and multiply to give me 6. They are in fact -2 and -3. So this factorization in the denominator is x minus 2 times x minus 3. Now that I've recognized that the denominator can in fact be factored, I have terms that will cancel. And I'm left with the limit as x approaches 2 of 1 over x minus 3. Well, now I can just plug in my 2, because this is equal to the limit as x approaches 2 of 1 over 2 minus 3, which is just equal to -1. So again, we start with a function that looks like it's going to be very troublesome. It looks like there's a place where the limit doesn't exist. It has division by 0. We're scared something may be shooting off to infinity or -infinity, making the limit not exist. But in fact, by using a little bit of factoring, I can recognize that this function is just 1 over x minus 3. And once I have it written as 1 over x minus 3, plugging in 2 gives me a very finite number. It is not infinity. It is in fact a value that will clearly be approached from the left and the right. It is a calculation for the limit.